Good morning, dear students. Welcome back to e-learning class. Myself Santosh Vijay. All dear students. In previous class, we discussed about the present and future trend of powder metallurgy technique and characterization of powder for PM process. Today shall be discussed with production techniques for PM process and powder shaping and sintering for the PM process. I hope you understand that. So techniques of the powder techniques as well, shaping and sintering methods. Let's begin the session. Dear students, let us discuss the production of metal powders. The selection of materials in powder metallurgy is determined by two factors. Number one, the alloy required in the finished part. Number two, the physical characteristics needed in the powder. Both of these factors are influenced by the process used for making a powder. So look at the image, dear students. The powder metallurgy process flowchart, which involves three basic steps, which is number one, the powders, second one is processing, third is properties. Number one, powder, which involves powder fabrication, size and shape characterization of powder, microstructure study of powders, chemical homogeneity, and particle size. And second process is processing, which involves compaction, sintering, forging, or hot pressing. And third step is which involves about it is properties of the powders, or property calculation or property measurements. The density method, porosity calculation, ductility and strength measurements, and conductivity measurements, and other functional properties. Yes, dear students, there are numerous ways for production, powder production, which can be categorized as follows. Number one, mechanical methods for powder production. In that, number one, chopping or cutting, abrasion method, machining methods, milling, cold stream process. In second method, the chemical methods for powder production. In that, the reduction of oxide, precipitation from solutions, thermal decomposition of compounds, hybrid decomposition, thermic reaction, and electrochemical methods. And third methods which we involved here, which we can take the process in physical methods of powder production. In that, uh, water atomization, gas atomization, special atomization methods. The choice of a specific technique for powder production depends on particle size, shape, microstructure, and chemistry of powder, and also on the cost of the process. Let's look at the image. Is a schematic diagram of mechanical milling. We warp the action in a jar mill. The jar is rotated on its side, and the impact of the falling balls grinds the material into a powder. Yes, mechanical combination. In mechanical combination, which are involved in crushing, milling in a ball mill, a powder produced for the different materials, brittle materials in the angular form, and ductile materials mainly which is in the form of flaky and not particularly suitable for PM operations. And other method in communications, mechanical alloying method. So alloying means the powder of two or more metals are mixed in a ball mill. Under the impact of hard balls, the powders fracture and join together by diffusion. So called it is a alloying method or alloying of powder method. It's mechanical combination to obtain the fine particles. So dear students, as we can see, the image is indicate that to obtain the powder but fine powder particles from a mechanical combination method, The method of mechanical communication to obtain fine powder particles, as you can see the image, A indicates that roll crushing, B indicates that ball mill, and C is a hammer milling. Dear students, as we can see the image, so fine particle powders are formed by crushing the rulers, by crushing the raw materials. And second image indicates that the barrel is contains a number of ball mills. Those are hammer the powder particles to form or fabricate the fine powders. And the third image, as we can see, the C image, is that particularly that barrel, inside the barrel it has a hammering tool. That hammering tool is continuously hammer the materials to form a fine powder particles. Yes, dear students, as we can see the image, it's a mechanical alloying method. A mechanical alloying of nickel particles with dispersed smaller particles. As nickel particles are flattened between the two balls, as we can see the image 1 or A, the second smaller particles, as you can see the second image, the smaller phase impressed into the nickel surface, and eventually, as you can see the C image, is dispersed throughout the particle due to a successive flattening, fracture, and welding events. Let's discuss. Number one is a mechanical method, chopping or cutting. In this process, strands of hard steel wire in a diameter as small as 0.0313 inches are cut up to cut up into a small pieces by means of a milling cutter. This technique is actually employed in the manufacturing of cut wire shorts, which are used for pinning or short cleaning. The limitations of this process, which involves it would, however, be difficult and costly to make a powders by this method, and for this reason it is not profitable to discuss the technique in detail. And second method is rubbing or abrasion method. These are all sorts of ways in which a mass of metal might be attacked by some form of abrasion. In that, number A, rubbing of two surfaces. When we rub two surfaces against each other, the hard surface removes the materials of form of the surface of the soft material. So, image B of filling as a production method has been frequently employed, especially to alloy powders when supplies from the conventional sources have been unobtainable. Such methods are also used for a manufacture of coarse powders for dental alloys. The filling can also be used to produce the fine powders if its teeth are smaller, commercially not feasible. And the C, uh, scratching. If a hard fin is rubbed on some soft metal, the powder flakes are produced. The scratching is a technique actually used on a large scale for the preparation of coarse magnesium powders. The scratching a slab of magnesium with hardened steel fins, a revolving metal drum to the surface of which is fixed a scratching belt. The drum, which is about 8 inches in diameter, it rotates at a peripheral speed of approximately 2500 feet per meter. The slab of magnesium metal 14 inches wide by 1.75 inch thick enters through a gland in the drum casing and press against the steel fin. And D, the machining process. A machining process using, for example, a lathe or milling cutter in which the something more than just scratching is involved, since the uh, attacking tool actually digs under the surface of the metal and tears it off. On lathe machine, by applying a small force, we get a fine chips. A large amount of machining scrap is produced in a machining operations. This scrap in the form of chips and turning can be further reduced in size by grinding a small scale production. The disadvantages of this process, if you look at the disadvantages of this process, a lack of control on a powder characteristics, definitely, including the chemical contamination such as oxidation, oil and other metal impurities. The shape of the powder is irregular and coarse. The advantages of this process are: for consuming scrap from another process, the machining is useful process. Presently, the machined powder is used with the high carbon steel and some dental amalgam powders. Yes, commercial method. Here we can discuss on commercial method, that is the okay, these are the methods used for a high production rate. Best example of mechanical production methods are the milling process and cold stream process. In milling, the basic principle of milling process is the application of impact and shear force between two materials, a hard and soft, causing a soft material to be ground into a fine particles. The milling techniques are suitable for the brittle materials. The two types of millings are ball milling and attrition milling. The main objectives of this process is the particle size reduction, comminution or grinding, the shape change, flaking, a solid state alloying, mechanical alloying, a solid state blending, a modifying, changing or altering the properties of a material in terms of density, flowability or work hardening, mixing or blending of two or more materials or mixed phases. As we can see the image, dear students, the ball milling is an old and relatively a simple method for grinding the large lumps of materials into smaller pieces and powder form. The principle of this process, the principle is simple and is based on the impact and shear force. The hard balls are used for mechanical comminution of brittle materials and producing the powders. As you can see, the image at the right side is a milling unit. The basic apparatus consists of the following: a ball mill or jar mill, which mainly consisting of rotating drum line from the inside the line from inside with the hard materials. As you can see the inside hard materials, this is, as you can see, is a drum. The hard balls as a grinding medium which continue to impact the materials inside the drum as it rotates or rolls. As we can see the schematic diagram for the tumbler mill used for milling the metal powders. Let's discuss the important parameters of a milling process. The most important parameter to consider the speed of rotation of the drum. An optimum or critical speed is adjusted for maximum impact velocity. The critical speed is the process above which the ball will centrifuge. A very slow speed of rotation will not carry the balls to the top. These will rock back down the drum side. A very fast speed higher than the critical speed will not let the balls drop down as they will be carried around due to centrifugal force. Thus, an optimum speed is required. The speed of rotation varies with the inverse square root of the drum diameter. The second parameter is that the material of grinding media and its size and density. The size and density of the milling media is selected according to the deformation of fracture resistance for metals. For hard and brittle materials, large and dense media is used, whereas small balls are used for finer grinding. As a general rule, the ball should be small and their surface should be a little rough. The materials of the balls and lining of the drum should be same as that of the material being ground. And third important factor is the rate of milling of powder is a function of quantity in the total space between the ball. And fourth important parameter is lubricants and surface active agents are used to nullify the welding forces which causes agglomeration. Now we will discuss the grinding mechanism. During milling, the following forces cause a fracture of material into powder. Number one, the impact force. These are caused by the instantaneous striking of one object on the other, which means the impact is the instantaneous striking of one object by another. The both objects may be moving or one may be stationary. Second important factor is shear force. These are caused as one material slides or rubs against the other. So the limitations of this process, which are rubbing action causes the contamination of powder since balls may also get rubbed. A working hardening of metal powder is caused during milling. There is a possibility of excessive oxidation of final powder. A quality of powder is poor. The particle welding and agglomeration may take place. The next technique, dear students, that is cold stream process. This process is based on impact phenomena caused by impingement of high velocity particles against the cemented carbide plate. The unit consists of a feed container, a compressor capable of producing high velocity stream of air, 56 meter cube per minute, operating at 7 megapascal. A target plate made of cemented tungsten carbide for producing impact. A classifying chamber lined with a tungsten carbide, while the supersonic nozzle and target generally are made of cemented tungsten carbide. The mechanism of this process is the material to be powdered is fed in the chamber and from there falls in the front of high velocity stream of air. This air causes the impingement of materials against the target plate, where material due to impaction is shattered into the powder form. This powder is sucked and is classified in the classifying chamber. The oversize is recycled and fine powder is removed from the discharge area. The rapidly expanding gases leaving the nozzle create a strong cooling effect through diabatic expansion. This effect is greater than the heat produced by the pulverization.
Dear students, as we can see the image, the raw material steam impacting a target and shattering in cold stream impact process. So let's move on to the next method to produce the powder particles, that is which is the gas atomization technique. The gas atomization technique is produce the liquid metal stream by injecting the molten metal through a small orifice. The steam is broken by jet of inert gas, air or water. The size of the particles formed depends on the temperature of the metal flow rate through the orifice, nozzle size and jet characteristics. So as we can see, this is the gas atomization method. The basic principle of this gas atomization process is that a high velocity gas stream flows through expansion nozzle, siphoning molten metal from below and spraying it into a container, which means, dear students, as we can see the molten metal inside the container, then which flows towards to the nozzle by means of siphon action, which are then fed into the nozzle neck. Subsequently, other side, they are passing the pressurized gas. That pressurized gas is passes through the nozzle, which means immediately it strike the molten metal. Once the molten metal are struck by the high pressurized gas, they turn into a small droplet, as we can see the droplets of the molten metal, which are then fed into the bottom collector. Then the solidify process is begins after solidifying, which will get the fine powders at the bottom collector. Hope you understand how it works. Dear students, as we can see the image, this is the horizontal gas atomization technique. The schematic of horizontal gas atomization. The technique is the best suited to forming the powders from the low melting temperature metals. Dear students, this is the suitable for the low melting temperature metals. The melt is siphoned into a gas expansion nozzle, the sprayed into droplets, then solidified and captured in an adjacent chamber. Yes, dear students, this, as I can explain earlier, this is works on the same principle. So see here, this is the molten metal which is in the container. The by means of siphon action, this molten metal is lift up and which are then fed into the nozzle neck. Subsequently, gases passes through the same nozzle neck, which means the pressurized gases are strike the molten metal. Once strike the molten metal, that molten metal is turned into a droplets, which are then fed into the bottom collector. After solidified, which will get the fine powders at the bottom chamber. And hope you understand. Just look at the figure, dear students. This is the vertical gas atomization. A vertical gas atomizer. The main features are the vacuum induction meter, gas expansion nozzle, gas recirculation and supply system, the feed light chamber and a powder collection chamber. An extended view of the nozzle region is given to show in the close proximity of the gas and melt streams needed for efficient atomization. This is the vertical type of gas atomization. The working principle is same as we can discuss it early. So here molten metals are here. This is the molten metal chamber. Dear students, here the molten metal chamber, the molten metal from the chamber, which are then fed into the nozzle neck. So subsequently the gas is supplied from the high pressure gas is supplied to the nozzle through the nozzle by the gas source, which means the gases are strike the molten metals. The fine powder which are then, once the gas is strike the molten metal turn into the droplets. The fine droplets are collected at the side of the collector, which is called as a fine powder collector. The coarse powder particles or coarse droplets are collected at the bottom chamber, which is called as a bottom collection chamber. Details of
droplet formation. Dear students, as we can see the image on the slide, this will given the detailed information how the particles are formed, and which is also called as the mechanism of formation of the particles. Dear students, as we can see the image, so here the molten metal is struck by the high pressurized gas. After that liquid metal is turned into a sheet structured, and after sheet will be turned into the ligaments. After the ligaments, which will form a ellipsoid, which is also called as a coarse grain size of the particles. After finally we can get the particular sphere type of the particles that will be collected at the bottom of the chamber. Hope you understand this is the mechanism of droplet formation. And coming to the next is electrode centrifugation. As we can see the image will explain the electrode centrifugation. Let us discuss the working principle of electrode centrifugation, how it works. A consumable electrode is rotated rapidly in the helium filled chamber. Okay, the rotating electrode is melted by an arc using a tungsten cathode or plasma torch. A centrifugal force breaks up the molten metal or molten tip of the electrode into the metal particles. The powder is formed from a melt electrode and is solidified in a vacuum or inert gas environment. Yes, let's move on to the next method to produce the powders, which is a chemical method. So almost all metallic elements can be produced in the form of powders by suitable chemical reactions or decompositions. The mostly chemical methods are based on the decomposition of a compound into the elemental form with heating or with help of some catalyst. In most cases, such processes involve at least two reactants, which are a compound of the metal reducing agent. The one example we will take here, that is the production of iron powder by reduction of iron oxide. It's also called as a direct reduction process. The iron powders are commercially used for a large number of applications such as a fabrication of structural parts, welding rods, of flame cuttings, food enrichment, and electronic and magnetic applications. The classical technique of the production of iron powder is the reduction of iron oxide. Let us see the theory of this process. It is the oldest process of production of iron powder by using a carbon as the reducing agent. In this process, the pure magnetite Fe3O4 is used. The coke breeze is the carbon source used to reduce the iron oxide. Some limestone is also used to react with the sulfur present in the coke. The mixture of the coke and limestone is round about proportion is around about 85% of coke and 15% of limestone is dried in a rotary kiln and crushed to uniform size. So called it is Honos process. As the the ore and coke limestone mixture is charged into a ceramic tubes, which is mainly made up of silicon carbide, with care so that ore and reaction mixture are in the contact with each other but not intermixed. It can be achieved by using a concentric charging tubes within the ceramic tube. Within the hard tube, the several chemical reactions occurs and metallic iron is formed in the form of a sponge coke. If the magnetite ore is used, then the following reactions will take place, as you can see on the slide, dear students. The decomposition of the limestone generates the carbon dioxide, which oxides the carbon in the coke to form a carbon monoxide.
The ferrous iron oxide is further reduced by the carbon monoxide to the metallic iron. The desulfurization occurs in parallel with the reduction of reaction between the gas and sulfides present in the ore, resulting in gaseous sulfide compounds which in turn react with a lime to form a calcium sulfide. The sponge cook is removed from the ceramic tubes and drops into a tooth crusher where this is broken into pieces. After these pieces are ground to desired particle shape, during grinding the powder particles are considerably work hardened. The powder is annealed at 800 to 870 degrees Celsius in the atmosphere of dissociated ammonia. The, the powder is loosely sintered but requires only a light grinding and screening to produce a finished product. The one more process is the carbonyl process, the only method for the manufacture of metal powder by the pyrolysis of gaseous compounds, which has been used industrially on a substantial scale, is the carbonyl iron ore nickel process. When the iron and nickel ores react under high pressure at around about 70 to 300 atmospheric pressure with the carbon monoxide, the iron pentacarbonyl ApCO5 or nickel pentacarbonyl NiCO4 is formed respectively. The both compounds are liquids at room temperature. Round about at room temperature, and pentacarbonyl evaporates at 300 degrees Celsius, and uh, nickel tetracarbonyl is around about at 43 degrees Celsius. The carbonyl iron powder is used for the production of magnetic powders or for radio or television applications. In PM, it is used for the manufacturing of soft magnetic materials and permanent magnets. Because of its high price and poor die-filling properties, it is not suitable for the manufacturing of sintered structured components. The carbonyl process is also well suited for the extraction of both metals from lean ores. The process can be controlled so as to yield a spherical metal powder. That one more chemical process for producing the powders, which is a precipitate formation. The steps of the process is carried out according to the following scheme. The liquid carbonyls are sorted under pressure in tanks submerged in water. The distilled and filtered liquids are conveyed to steam heating cylinders where they are vaporized. The vapors of liquid are sent to the decomposers. The decomposers are jackets and heated, giving an internal temperature of 200 to 250 degrees Celsius. These cylinders are 9 to 10 feet high with an internal diameter of 3 feet with a conical bottom. The incoming stream of vapor meets a tangential stream of ammonia gas. The CO is removed here and precipitate of the metals are formed, which are then sieved, dried, and may be milled to break up the agglomerates. The CO gas arises from the decomposition is recovered and reused. The reduction of metal oxide. The manufacturing of metal powder by the reduction of oxides is extensively employed, particularly for
iron, copper, tungsten, and molybdenum. Mainly so here we are figure out some advantages of the reduction of metal oxide. The variety of the reducing agents can be used and processed can be economical when carbon is used. A close control over particle size. Porous powders can be produced which have a good compressive properties. The adaptability either a very small or a large manufacturing units and either a batch or continuous process. So limitations we figured it out here. Some limitations of this process are the process may be costly if reducing agents are gases. The large volumes of reducing gases may be required and circumstances vary where this is economically available may be limited. In some cases, however, the costs may be reduced by the recirculation of the gas. The purity of the finished product is usually depends upon entirely upon the purity of the raw material, and economic or technical consideration may set limitations to that which can be attained. Live powders cannot be produced. Okay students, now I will stop this session. We will continue to the next topics in the next session. Hope you the session was utilized, and we will discuss the left out topics in the next session.